Hi, in this video we're going to talk about optimization problems. There is a whole class of problems where you try to minimize or maximize a particular value. These problems are going to be related most of the time to some kind of a real-world situation, and there is a lot of varieties of different problems, so algebra here is extremely important. So what are the steps? First of all, we're going to read the problem and understand what quantity we're trying to minimize or maximize. Then we're going to need to write an algebraic expression for that quantity that's going to use only one variable. Then we're going to apply the first derivative test, which will allow us to find where a quantity, where our function is going to have a max or min. And then we're going to reread the problem and answer the question. So with this example, it's a very common example. Jim has 180 feet of fencing and wants to enclose a rectangular pen. What dimensions are going to yield the maximum possible area? What is the maximum possible area? Let's sketch some possibilities first of all so we can understand what we're dealing with. So we have a total of 180 feet. What can we have? Well, we can have an enclosure that's going to be 30 feet here and then 60 feet here. In this case, the area is going to be 30 times 60, which is going to be 1800 square feet, right? 30, 30, 60, 60. That's going to give us a total of 180. Okay. What's another possibility? Well, we can have, what else? We can have 40 here, and we can have 50 here. So in this case, the area is going to be 40 times 50, which is 2000. So it is more than in this case, but we still don't know if it's going to be the maximum possible. Alright. So I'm going to do it algebraically. So what do we have? We have an enclosure that's going to be rectangular in shape. So if we label this as x, and obviously that's going to be x, and we know the whole thing is 180, so we know that between these two sides is going to be 180 minus 2x, and if you divide it by 2, that's going to give you 90 minus x. So this side here is going to be 90 minus x, and this side here is going to be 90 minus x. Okay? And then we can write the formula for the area. The area formula as a function of x is going to be length times width, x times 90 minus x, which we can rewrite as 90x minus x squared. So, the first derivative test now. A prime of x is going to be 90 minus 2x, just like every time we use the first derivative test we set it equal to 0, and we can see that our critical point is going to be 45. Now we do need to see if it's actually minimum or maximum. So we'll make a number line, put 45 here, and determine the signs of A prime. So to the left of 45, the value is going to be positive. To the right of 45, the value is going to be negative, which means A of x is increasing here and then decreasing. So that is a max, right? So the dimensions will be, so it's going to be 45 by what? 90 minus 45. So it's 45 by 45, essentially it's going to be a square. And the maximum possible area is going to be 45 times 45, which is going to be 2025 square feet. Okay, so again, let me run quickly through what I did. So we sketched the problem, it's always helpful. Most of the time sketching this, especially when the geometry-based problems, is going to be helpful. We expressed one of the dimensions of this pen using x, and the other one was expressed by realizing that the whole thing is 180, so we were able to find that the length is going to be 90 minus x. Then we wrote the formula for the area using that variable x. We applied the first derivative test, and we found that the critical point was 45, and we determined that this is a max, and that's what it was. Okay, so there is a variation of this problem So Jim decides to use 180 feet of fencing, but he's going to put it along a barn wall. This way he doesn't have to put the fence there, so he can use more fence. Okay. So in this case, the picture is going to look like this. So this is our barn wall, and we're going to have our enclosure going like this. So how does that change? Yes, we still have 180 feet of fence, but if I say that this is X and this is X, then this length here is going to be 180 minus 2x, correct? Because then the whole thing will be 180. Remember, we do not have any fence here. We use the barn wall. So we write the formula for the area in this case. So area as a function of x is going to be x times 180 minus 2x. And then we differentiate that because we're going to need to use the first derivative. Well, actually, hold on a second. Before I do that, let me write this. I got a little bit ahead of myself. No differentiation yet. I'll get to that in a second. So we're going to write that as 180x minus 2x squared. Now we can differentiate that. So a prime of x is going to be 180 minus 4x, and we're going to set it equal to 0. So in this case, the value of x is going to be 45, but let's see if it's actually a max. By the way, do not ever assume that if you're going to come up with a specific value, it is necessarily going to give you what you're looking for. So you always need to verify. So 45. So a prime of x is going to be positive here, it's going to be negative here, so we know that a of x is increasing and decreasing. Yes, this is a max. So what are the dimensions then? So in this case it's going to be 45 by 180 minus 2 times 45, that's going to be 90. So it's actually going to be 45 by 90 feet. And the maximum possible area in this case is going to be 45 multiplied by 90, which is going to give us 4,050 square feet. Okay. So again, same exact idea. We drew a picture to help us see the situation better. We wrote the formula for the area using one of the variables, so we decided that we're going to call this x, and then this can be expressed as 180 minus 2x. Then we differentiated, set the derivative equal to 0, found the critical point, verified that this critical point is a maximum, and we were able to answer the question. Okay, so let's go ahead and take a look at another problem. So Miguel wants to fence two equal-sized side-by-side pens, as shown in the diagram below. So in this case, he wants to enclose 600 square feet, and what is the minimum possible amount of fencing that he's going to need? So remember, he has fencing going here, 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 and just one time here. So what do we know? If we call this length and we call this width, then we know the length times width must be 600 square feet, correct? So if I use x here instead of, so let's say w is going to be x. So then I can rewrite that as Lx equals 600, and I can express the length, which is going to be this here, as 600 divided by x. So my function for the fence, let's call it f of x. So what does it consist of? So I have x here, I have another x here, and I have another x here, right? And this is going to be 600 divided by x, and this is going to be 600 divided by x, correct? So I have 1, 2, 3, 4, 5 different pieces. So I'm going to have x 3 times, so 3x, plus this and this twice, so 2 times 600 over x, which all is going to be 3x plus 1200 divided by x. So this is our formula for the length of the fence right here, and we're going to differentiate that. So f prime of x is going to be 3 minus 1200 over x squared. This is the derivative. Because we're going to set it equal to 0 and try to solve it, we need to bring it to a common denominator, which is going to be 3x squared minus 1200 divided by x squared. And I can factor out 3, and it's going to leave me with x squared minus 400 divided by x squared, and that all is going to be equal to 0. So, what are the critical points? It's going to be 0 and also plus or minus 20. Now, not all of them are meaningful, because x obviously cannot be 0 because then you will have no enclosure, and you also cannot have a negative value. So the only value that we are really interested in is going to be a positive 20 that we're going to consider. We still don't know if it's a max or a min, so we'll have to check, or even not necessarily even anything. So we're going to put 20 here, we're going to put f prime of x, and then when you check the signs of the derivative, you are going to see that it's going to be negative here and it's going to be positive here. All we do is we substitute a value to the left of 20 and to the right of 20 into our derivative, and you can see it. Okay. So then what do we have? A minimum amount of fencing. So what is it going to be now? You need to be careful because 20 is the value of x. Okay. But we need to know how much total fencing we're going to have. So it's going to be 20 here and 20 here and 20 here, right? So it's going to be 20 plus 20 plus 20, and then plus, you're going to take 600 over x, which is going to give us 30, and 30 times 2 is going to give us 60. So you're going to have a total of 120 feet of fencing that will allow you to, that would be the minimum possible amount of fencing with which you will be able to enclose 600 square feet. Or square yards, I should say. That's yards. Alright. Next problem. So this is a very well-known problem. When you have a rectangular sheet of cardboard and you want to make an open top box, you're going to cut out squares and you are going to fold them up, and this will give you a box, and you want to try to maximize the area, and so you want to figure out how much you're going to cut at each corner. So this is our 5x8 sheet of cardboard. So we're going to cut out this much at each corner. Let's call it x. Okay, so what we need to figure out now is we want to see how we can represent the length and the width and the height of this box, because we're trying to work with the volume, right? So let's see. If this is going to give me the base of my box, so the whole thing is x, I'm sorry, 8, and we're cutting out x here and x here, so this here is going to be 8 minus 2x, and for this distance here, the whole thing is 5. You cut out x here and x here, so it's going to be 5 minus 2x, correct? And then when we fold, let me show you, a sketch a little representation of this box. So this is going to be x, This is going to be 5 minus 2x, and this is going to be 8 minus 2x. These are our dimensions. Then we can write the expression for the volume. So the volume here is going to be length, the height, and the width multiplied together. So I am going to write what this is going to be once everything is multiplied. This is going to be 4x cubed minus 26x squared plus 40x. So this is the volume function, and now we are going to differentiate that and see what we get. So v prime of x is going to be 12x squared minus 52x plus 40. We're going to need to try to factor it. So the first thing we can do is we can factor out 4, which is going to give us 3x squared minus 13x plus 10. And that can actually be factored, the trinomial here. So it's going to be 4 times 3x minus 10 times x minus 1. I'm going to set it equal to 0. So we see that we're going to have two critical points. We are going to have, one of them is going to be 10/3, and the other one is going to be 1. Now, before we start analyzing these numbers, because it's two different values, we need to think, are there any of these values that are not going to make any sense? Let's see. 10 over 3 is 3 and change, correct? So think about this. If I'm cutting 3 and change out, but I only have 5 inches going this way, I can't possibly make a cut that's going to be 3 plus inches from one side and 3 plus inches to the other side. That's already going to be over 6 inches, and I only have 5. So this value does not make any sense. It is a critical point of our function, but in the context of the problem, we cannot use this. So 1 is the only value that we can actually look at. So what do we have? We're going to have 1. It's going to be v prime of x. And the signs will be positive here, negative here. So it's going to be increasing and decreasing. So we know it's a max, right? So what are the questions here? How much do we need to cut in the corner? So we're cutting 1 inch. What dimensions are going to give us maximum possible values? So dimensions are going to be, so the height's going to be 1. So this is going to be 6 by 3 by 1. And the volume, maximum possible volume in this case, is going to be 18 cubic inches. Okay. So this problem obviously is more advanced than the other one, because we already end up with the quadratic function. I mean, in this case it's a cubic function, so it does make it a little more challenging, but the idea does not change. You still drew a picture to represent the problem, wrote an algebraic expression that represented the quantity we were trying to maximize in this case, and we solved it. Alright, moving on. So we have a rectangular fish tank. It needs to have a capacity of 32 cubic feet. The tank has no top, so it's an open top. The base is going to have to be a square. That's how we want it. And what dimensions are going to yield the minimum possible area? This way we're going to use the least amount of glass. So let's start by making a picture. Remember, pictures are always good if you can draw them. They give you very good visual representation of the problem. So if we think that this has to be a box that's going to have a square base, and we can say that this is going to be x and this is going to be x. So then how do you write the expression that's going to represent the height? Because remember, we use only one variable. So in this case, we know that x squared, let's call it h, times the height has to equal 32. So that means from here we can conclude that we can write the height as 32 divided by x squared. So now the challenge is we have to write the surface area. So for the surface area, it's going to consist of what? It's going to consist of one square base and then four side faces, right? So then a of x is going to be, so the area of the bottom is going to be x squared plus 4. How do you write the area of the top? The area of the top is going to be this distance is x times the height, which is 32, over x squared. So this whole thing is going to be x squared plus 128 over x. So this is our area formula, and we can now go ahead and differentiate that. So a prime of x is going to be 2x minus 128 over x squared. We want to solve this set it equal to 0 and solve this as an equation, so let's bring it to a common denominator. So it's going to be 2x cubed minus 128 divided by x squared, and we can factor out 2, and we're going to get x cubed minus 64 divided by x squared. So we set it equal to 0. What are the critical points? We're going to have x equals 0 and x equals 4. X equals 4 is the only real solution of the equation x cubed minus 64 equals 0. So that's the only one we're going to consider. X equals 0 will not make any sense in the context of the problem. You will simply not have a tank. So we are going to reject that. And then we're going to go ahead and use 4. So 4, a prime of x. So what do we have here? Once we substitute this value, we're going to see that it's going to be negative here and positive here. That's decreasing, then increasing. So it is a minimum. So then what do we have? What dimensions are going to yield the minimum possible surface area? So the dimensions are going to be, so we're going to have 4 by 4 by a height, which is going to be 32 divided by 16, which is going to be 2. Right? And the least area is going to be then, you simply take this value of x equals 4 and substitute it into the function. So it's going to be 4 squared plus 128 divided by 4. And that's going to give us 48 square feet. So 48 square feet will be the minimum possible surface area of that tank. Alright, so I do have one last problem for this video. So a metal cylinder needs to have a volume of 250 pi cubic centimeters. What dimensions are going to yield the minimum possible surface area so we can use the least amount of sheet metal? And what is the minimum possible surface area? Okay, so it's a cylinder. Alright, so in a cylinder, let's say that we have a radius here, that we're going to call r, and this is going to be h. So how do you find the volume of a cylinder? It's pi r squared h. But we need one variable, so what do we know? We know that the volume is going to be it's going to be 250 pi, and it's going to have to equal pi r squared h, because that's a fixed value for the volume. We can see that pi is cancelled, and we can from here determine that h is going to be 250 divided by r squared. Okay, and now we have to write the expression for the surface area. So the surface area of the cylinder is going to consist of two parts. There's going to be two circles, so it's going to be 2 pi r squared plus, and then there's going to be the sides, which is going to be 2 pi r 2 pi r h, right? But remember, we have to replace h with this because we want to have only one variable, so it's going to be 2 pi r squared plus, once you substitute this here, it's going to give you 250 divided by r, right? 2 pi r squared. It is going to be, hold on, it's going to be 500. Yep, 500. So we're substituting h right here. This quantity was substituting it in here. And after you do algebraic work, you're going to get 2 pi, let me rewrite this. So it's 2 pi r squared plus 500 divided by r. Okay. So we go ahead and differentiate this. So a prime of x is going to be 4 pi r minus 500 divided by, hold on, I think I'm missing pi here. Yep, there's pi here that I need to have. Yep, 2 pi rh, correct. So 500 pi divided by r squared. And we are going to need to bring it to a common denominator, combine them together so we can solve this. So this is going to be, rewrite, so it's going to be 4 pi r cubed minus 500 pi divided by r squared. And we can factor out 4 pi, which is going to leave us with r cubed minus 125. Reminding you, 4 pi is going to be a constant, so we don't even have to worry about that, divided by r squared. And now we set it equal to 0. So critical points here are going to be 0 on the bottom and also 5. 0 again will not make any sense, we will reject that, but we will check 5. So 5 here. And let's see, you're doing a prime of x. Once you check the signs, you will see it's going to be minus here and plus here. So it is indeed our relative min. So then what are the dimensions that's going to allow you to use the minimum amount of sheet metal? So the radius is going to be 5 and the height is going to be 250 divided by 5 squared, so it's going to be 10. And what is going to be the least amount of surface area? Once you plug it, just take this value of 5, substitute it into this formula here, and you will see that it's going to be 150 square centimeters. This is centimeters and centimeters. Okay, so it's just an introductory video. There are more problems and I'm going to be making more videos on more advanced problems, but I hope this was helpful.